I think shared beforehand, there would be what the dev is the schematic of the system. So if people want to discuss that afterwards as well, there's no other thing. So we need to mute the, or maybe I can mute it. Oh, it's muted now. Well done. Thank you, systems administrator. Okay. So no echo. So no, without any ado, the over to yourselves. I said loud breathe. Say it, you breathe. You like to please start it. Right button to the right sequence. Okay. Very good. So first of all, we turn the cooling fan on. There we are. Now start yours. And then we'll start to see the screen, but then it will not forget. Make quite a dry day here, and we're just using pure air for this experiment or this presentation. So we're not adding anything like air, I mean moisture and water, etc. So so it's quite dry. So it's interesting. Just the ambient humidity in the air has maybe a 10-20% change to the COP. The initial humidity of air is very important factor. That's absolutely yes. But here we're not. We're just showing pure air on this test. That's right. Mhm. And afterwards, we can share the readout. We're recording the screen readout, and there's some different views. So one shows the comp basically is more of a continuous straight line. So we'll share that afterwards rather than a dancing number. And this is an open loop system, so it's just the air from the laboratory going in at the moment. Well, you have there's another one here which is closed loop. So we do that basically. We can do a whole range of different gas mixes on there, and we can analyze the gases that are being produced as well. So there we are. Anyway, it's been running for a while, so if you don't mind, it's quite noisy in the lab. I'll ask them to turn it off, and then I'll go to another room for the Q&A. And not on, and not on, but I need them off. Yeah. But is there a camera closer to the device? Is there what? Camera. To see what is going on? Yes, it's called Salome. It's the camera. It's Salome. It's the video called Salome. 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 I can start it again if you want to see it. You can blow that camera up on your screen.
I wasn't able to blow it up, so can you see?
Yeah, okay, restart. Hold on a second. We just got a thumbnail image. Oh, sorry, I didn't realize that. I was using pin, and that seemed to work. Okay, so and there we go. Right, and pin. Pin, is that right? Pin. So I did right click and then pin. Can people see it much clearer now?
Right click and pin works for me too.
Okay, so we'll turn it on again so people get, and then people can also do the same trick for the lab computer screen as well. Yeah. That works. Let me just turn it off a couple more minutes whilst people have a look on the active first.
That's a cathode at the top, Aslan. Glowing there, bright yellow.
No, it's the anode.
Oh, sorry, of course.
Yeah, the system is all right, and then the cathode in the bottom.
Right.
So the cathode and the catalyst are combined.
It's fine. I remember.
The white beacon. Hassan, can you say anything about the durability of the cathodes? I mean, how fast are they eroded or destroyed by the plasma? I'll answer that when the noise is off, if that's okay. Okay. They'll be lasting a lot longer than we are doing at the moment because we haven't got the fan speed correct. It's sticking on one at the moment. It's sticking on one anode. It should be rotating faster. You see, when we started, the cops are lower, and then as the dust heats up, get a slightly higher cop. And this, I'll explain when the camera's off why the cop here is a direct cop. It's not comparing it to the control. The control is about 0.75% efficient. You do all the losses. So when it says 3, it should be 4 approximately on a real cop. We're off now. Yeah, we got it now, yeah. Yeah, decent products. Okay, so I'll go around this way and go and sit in the other room. Hey. Yeah, come on in. Come on in. It's so I'm gonna put it there and get my stream out. But yeah. Can I any consider we like this? It's one done. There are people like Beatrix, thank you very much. So put some here. Maybe there we are. Hey, that's a lot quieter now. So Jean-Paul, I'll answer your let me just take this pen off again. Okay. So Jean, answer your question about electrode wear. The when you get the vortex going correctly at the right speed, it should basically be then switching electrodes. So the electrodes don't get one electrode is working, then switch to the next electrode. It goes round. That is one way to decrease the ablation of vaporization of the electrodes.
The other way to do it is we've been basically designing a magnetic ring to go around it, so we can basically rotate it magnetically. The third way of reducing that is we basically not in this lab at the moment. We haven't got it turned on, but there's a pulse generator. And with the pulse generator, we can increase the copper considerably. And that means that we can also reduce the overheating of the electrodes considerably doing that, because we fire a burst of electricity in an impulse. We then wait until the linear effect dies down for a millisecond, and then we can hit it again with another impulse. So that way, we're not constantly having to keep the electricity supply going. And those are the three ways in this device of how to minimize the electrode abrasion. And the electrodes, I think, are like 100,000th of the cost of the machine. They're an insignificant part of the actual operating cost, but yeah, it's an important thing that we're working towards. Is electrode wear and tear. So yes,
Okay.
yeah. We're also working on the energy. We're also working on the energy recovery mechanism as well. So at the moment, we're at, say, COP, or for example, on the device here, you connect a 50% efficient energy recovery device to it. In this case, a basic steam, a multi-stage steam engine at around 50% efficiency. So we can then produce electricity coming off the device, and we can then use it for powering the machine. But our main applications that I mentioned to Jean-Paul when he was here, the main applications we've got around here are all industrial heating. So we're working towards an industrial heating solution. Yeah, Michael, go ahead.
Sure. The electrode, it's not participating, so you could use the material that will erode the least, like titanium, for example.
Yeah. For example, titanium is a good one. Yeah, basically that it's currently eroding, even if it's slowly eroding. We get it wrong, and there's not enough coolant being supplied, or supplying too much electricity. Yeah, they just vaporize off. So, and in the closed loop system, that titanium is just going to go around in circles and turn into aluminium or something different.
But there might be a way that you can then redeposit the titanium while the device is in operation, rather than taking it out of operation.
Or we could use a feeding wire, for example, so no, it can be turned off. Yeah, everything have that screen back. Sorry. So it'd be better to have a feeding wire going in. These are feeding wires from for welding machines anyway. So yeah, we could just feed the wires in. They're all.
You could just keep going. In other words, the device doesn't have to come offline as long as you're feeding the wire.
Yeah, exactly. And one of our colleagues in another lab, he basically got like a water-cooled electrodes working as well. So yes.
Okay. So then
It's so much of this is just either an electrical engineering problem or a systems engineering or a mechanical one. Yeah, I think everyone will be debating the science for years. I'm sure Anatoly's got a much better idea than I have on this science, but
wait a minute. Is the erosion of the cathode due to weathering or due to evaporation?
Very good. Very good. It's not the cathode, by the way. On
The anode, yeah. Okay.
The anodes. Good question. I'll ask a techie in the lab, and he'll come back to you with costs. So, yeah. Paul, go on. You've been a hand raised. Go on.
and did you try? Oh, sorry. Go ahead, Bob.
Sorry, Jacques.
Can you hear me?
Yeah, I got you nothing too.
Okay, so you're using for the anode the fed tungsten wire.
It's one of the
Or titanium wire.
Yeah, it's titanium or tungsten.
Okay.
You can use You can use both.
That's okay. For those people, there's a few people in the room that know how you calculate your COP, but I didn't hear a summary of how that is done. Are you measuring first the power input from the wall as the denominator?
No, we're not. We're doing both. We're measuring, well, the power is one is measuring the power into the whole system.
Mhm.
And 90% of the system, well, the system is basically two main energy consumptions in the system for getting the controllers and sensors, which are nothing, is the fan, power plug, and the power supply unit.
Mhm.
So we're measuring at the moment, we're showing that COP you're sitting on the screen in what is DC. It's directly going into the energy cell. And I think when Jean Paul was here, we've also got different watt meters showing different energies going in. I'm making an apology for this. So the apology for that is that we could show that COP as the complete system COP, and we can maybe run that again another time. We can show you that. When we're running the power, we have power supply unit, for example, that's 5 kilowatts of a power supply unit. Its operating performance. If you run a power supply unit at 90% of its efficiency, it's most efficient. When you run it at 10% of its output capacity, it's really inefficient. It's like down to 50% efficient. So, but because we're running this in a lab machine now, these energy cells, they mainly produce, some of them produce heat mainly, and some of them produce pure electricity, or almost pure electricity coming off them. Now, even the one you just seen, which is just running air, is producing heat mainly. Then it's still producing some electricity coming out. And that fries the circuitry in the units. So what we try and do is buy a power supply unit that's really powerful, so it's less delicate inside, so we don't fry some of the more sensitive components. And so that's why we're running in the lab a big power supply unit, relatively power supply unit for a small input power, is just because there's some ruggedness, redundancy.
Yeah, I understand that. So, what is the input power relative to the? Sorry, I was only looking at the COP in that brief demonstration. So, what was the input power as a proportion of the rated power supply?
I think we're running at around 70% efficiency on that. So we're putting in, for example, 1 kilowatt going in, out of the DC unit, i.e. to the energy cell, we'll be putting 1.3 kilowatts into the actual power supply unit.
Okay, so you're measuring your total input power is your discharge in and your fan in, but not the overall system control.
We're not showing fan. For
Okay.
example, at the moment we can run. It's just how the instrumentation's in at the moment. The fan is using one second. Let me just check with guys.
Yeah, no worries.
Being shown on the screen as well.
Yeah.
Well, tell you.
Right, now we can talk amongst ourselves.
James. No. Yes, you did.
You're like my next question, Anatoly.
Teleportation.
Well, the thing about the fan, Bob, is of course it's running at a fixed speed. It's
200 fan was doing 250 watts, so it was about 10% of the test. The output energy was the fan effectively.
Okay, so how are you measuring the output energy? Is that in some sort of calorimeter from the mass flow on the airflow, or you're doing some sort of Stefan Boltzmann on the outside of the tube, or a combination of both, or what?
Jean Paul. Jean Paul.
Going to have a cup of hot cocoa.
I had to put the mic on. Okay. Yes. Measure the power.
The power out. So we've established that the power in is essentially the discharge from a slightly inefficient power supply, which is overrated for the input power. But I'm trying to establish what the output that is determining the
What is rated by the delta T, the input, temperature F, input F, output, and the mass.
Okay, so you're excluding any thermal losses from the glass in Stefan Boltzmann sort of.
We don't include that.
Okay, have you done an estimation for that?
Yeah, well, what we done is we beforehand, we're doing like we put a nickel coil in there between the anode and cathode, and we run that, and that shows that the system is about 75% efficient.
Okay, all right, and then have you done some sort of estimation for the amount of magnetohydrodynamic electrical losses that are being radiated out from the discharge, or the electrical losses?
No.
Okay. Okay, so those are my questions on COP determination. The question on catalysts, are you using neutron absorbers, a bit like Anatoly?
On the calculus, I wouldn't know what a neutron absorber was.
So things like xenon, cadmium, hafnium, gadolinium, cobalt, samarium, titanium, which you are using, dysprosium, erbium, europium, molybdenum, or ytterbium.
And the human motor. That's like,
are you using any of those? I know you're using titanium.
Yet.
Okay. All right. So you're not answering, is what you're saying. Okay. All right. Those are my questions for now.
And it's not exotic. There's no exotics.
Well, none of those are exotic.
But actually, if that helps with your magnetohydrodynamic question, when I was at the lab some months ago with Aslan, they had the Portuguese Electrical Engineering Institute there, and they were looking for stray RF emissions and so on, and found virtually zero. Yeah.
Oh, that's a shame. It would have been a shame to have got some extra power out of it that way, or direct generation. Have you? What kind of radiation monitoring are you doing, and have you used any radiographic emulsions at different distances in group clusters?
Oh, Anatoly? I have a small question for you. What I don't know, what is using the question from Bob was, he wanted to know what emissions have you been using to detect coming out of the machine? Because I remember you were doing X-ray spectrometry on the machine at one stage.
Yes. For the answering for book questions, it's yet to know the answer for the very simple question. What's the typical value of air mass flow rate? Can you tell us the information about air flows or air mass flow rate? What's the typical value?
It was on there a minute ago. I'll go and ask. Hold on.
I'm not going to let him get away with the radiation question.
No.
Well, wait, be patient. I know. Thank you, Anatoly, for clarifying the mass flow rate.
Yes, because erosion gases depends on for air flow mass flow rate. If you have a huge value of this consumption or mass flow rate, the growing process is small. The containment is a small value of the this air flow wasteful rate. It's the erosion process depends on the gas flow rate.
Anatoly, 200 cubic meter in minute. 200 minute. 200 a minute.
200.
200,000 cubic meter. How much?
200.
Why do you do this? Why do you do it? You know,
200 liters a minute. I got that option on.
the great value of the gram per second, how much gram less under per second. That is it. Meters has it in there to
Anyway, and so you have to calculate afterwards, I'm afraid.
Okay.
And calculate it afterwards. You said how much? You said 200 standard liters a minute.
Liters.
liters per minute.
That's right.
Sorry, okay.
800 liters per minute.
Yeah.
Correct? It's 200 grams divided
It's very honest. Second.
seconds, about 2 grams per second.
Yeah.
Small value, very small value. The typical value is about 10 grams per second is the optimal value of the mass airflow mass flow rate. It's very small value. Couldn't quite be. It's not couldn't know it's good.
The new that came in on that test, we were doing 5 grams per second.
It's so much small value. It's not sufficient. If you increase this value, you obtain more better results with the shape of the pin.
I'll go it.
For example, for example, 10 grams per second is good value.
We'll try it afterwards, okay?
Try it down to 11.
And we could try other gases, like water vapor, for example.
Yeah, it's better. It's much better. Yeah.
Yes, and hydrogen.
Advanced?
Okay, it's not good.
Hydrogen's good. Yeah, so we can run different ones in the lab, but just for today, we were just running a nice, safe, easy, simple one. Obviously, it was too slow, so we'll turn the air up next time. Yes.
Are you cycling it through a heat exchanger? Is that what you were saying about the cooling device?
If we can, we have one unit in the lab we use for mixed gas experiments, and that has a car radiator fitted into it.
Okay, great. Now, can I go back to the question that was not answered? What radiation monitoring have you done, and have you used stacked nuclear emulsions at varying distances from the device?
We haven't used stacked nuclear emulsions from the device, but Anatoly, in Portugal, we've done alpha, beta, gamma detectors and a whole range of the normal electromagnetic radiation monitoring equipment you'd have the ions. We see never change the background radiation here, and we see only 5% of the static electricity type emissions you'd expect to see from a car, emission system.
According to my experience, main dangers from the core is they are connected with the checked X-ray radiation, connected with the erosion particles which inject with the open atmosphere. It's very dangerous to breathe this air, especially for the young people.
Yes, that's why we have a very fast extraction system around the exhaust. But yes, the X-rays, if we keep the cop down, like we're doing at the moment with this demonstration, then we're not seeing any change in the X-rays, soft X-rays coming out either.
Safety for using is very important for their using this type of the
and Bob, it's very important to keep the cop down whilst we're doing other detected demonstrations. When we're doing closed loop, shielded.
Yes, where it's a very good idea. Push it on the test of the
Exactly, thanks, Anatoly. Yeah.
And what shielding are you using?
What shield are we using? Apart from high boron contact glass at the moment, we also basically are able to put a metal shield around it.
Okay. Well, I still think unless you've determined what you're getting out of it, other than the standard radiations, which you typically don't see. It's interesting you say there's I know you've looked for gamma, but Anatoly in the Russian conference recently said that it reduces gamma emissions in the environment of a working reactor. Although you had a source, is that correct, Anatoly?
Is correct, but it's secondary results, but not the initial results. Initial results, the its existence of the top X-ray radiation emitted by the erosion nano micros micro particles from the cassette erosion. Because this particles is the simplest or when LENR rate.
Yeah.
Particle.
Yeah, so I think, Haslan, if you're going to have young people anywhere near it, and I'm not particularly sure or care what kind of shielding you think you've got around it, you need to identify the kind of radiation that he's talking about and that we've observed. And then you need to create appropriate shielding for that. So I can talk to you and help you with that.
Thank you very much, Bob. Thank you. Michael, please.
Yeah, we talked about gamma, and we talked about activated particles that radiate later. What about neutrons? Did we put a neutron detector next to the device to make sure it's not me and sending them outside?
We have neutron detectors in the lab. Anatoly, have you had neutron detectors?
Yes.
Yeah.
We use gamma and neutron detectors in my laboratory. It's very important. But the many version for us the study of the correct operation of this recorder of these devices in the condition of the plasma reactors operations, because these devices operates is not correctly in the during the getting experiment. It's need to study the correct names in detail in future. It's right. It's very important.
Lynn Bowen wrote me over the weekend because I asked her just to summarize, please, why you don't detect the neutrons outside the chamber, and she wrote a very nice report why you do not detect neutrons coming out for a number of reasons, including the boron in the glass. But she also said you need to really fine tune the neutron detectors to be able to try and detect the specific type of neutron or speed energy of the neutron coming out.
I would also suggest you look at Alexander Shishkin's modified boron-10 neutron detectors, where he looks for other type of charge clusters. He biases it negatively, I think, at 590 volts, and you get a 50 times signal, and the shape of the neutron pulse isn't because it's a neutron, and it's a much larger signal.
Yes, I agree with you, Bob. Because of it's a very difficult question for their understanding.
Yeah, I can help you with the source for that. I'm sure Anatoly can as well.
Bashira, thank you. Jean-Paul, you got a question?
Yeah, I have a question. Well, according to you, what's the mechanism? Because you have an air as oxygen, nitrogen, and water vapor, basically, and then you have the electrons. So where is the reaction happening, according to you?
Anatoly, where do you think the reaction's happening?
There are once more.
Is reaction happening on the anode, the cathode, or in between?
I mentioned about the main reaction zone directed is the erosion particles there, and creation of the erosion particles near the cathode area. Here the zone, here cathode electrode.
So that means it's linked to the voltage you are applying. The higher the voltage, better it is, or what?
the higher the impulse energy that is in.
Correct? Or what voltage you're using, the amplitude of the pulses.
Now the amplitude of the pulses I can't tell you, but I can tell you the voltage there was the average voltage there was 1,500 volts.
Yeah, so that's similar to the work of Suhas Ralkar and to the work of Bogdanovich.
But when you have high impulse, high amplitude pulsing, then you can basically create very good reaction zones in the area that Anatoly mentioned. And what we've been doing is we are, because we're based in the University of Aveiro in their campus, the Portuguese National Material Science Center is located on campus. And there they've got very good electron microscopy services there with X-ray spectrometry. So we've been taking the cathodes and anodes off, taking them over there, and then looking for the signs of transmutation, both in terms of specifically what the topography of those areas looks like and the chemistry of those sites. And there's definitely LNE specific NNER sites on the anode and cathode.
Yeah, it's the spatial arrangement that gives it away. Anatoly has often used spectral measurement as well for seeing over time how the elements change. Anatoly, could you describe some of that?
Yeah, I measure near typical optical spectrum when this discharge is the first method of his period for the study transmutation of the chemical elements in our data. And the second, we use water or water observation of these particles is water cool, and you share there. It is method for the measuring of the chemical species of the erosion particles. So, independent measure first of their optical spectroscopy measure, and the second the EDS or energy dispersion spectroscopy is used in our experiments.
Good point. Did you try to put the filter to recover this dust coming out of this?
Yes, we've done that. Not so much a filter, we've done like an electrostatically sticky film that's designed for such things and taken it across to the for analysis. So you see some interesting almost like nanocrystal structures on there and some elements that maybe shouldn't have been there.
Yeah, when we did a Mars gas on tungsten, we saw the same transmuted particles on the tungsten as we captured in the filter.
Yeah.
So it gives you a good cross correlation.
Yes, that's right. I mean, but also the problem is you've got a very high, well, not high enough, obviously, but then high flow rate coming through the reactor, so a lot of it gets blown off, basically out into the extraction system.
And it's true to say, by the way, that the exhaust does have the classic burnt metal smell that you can detect. So there is a physical, manifestation of that in the exhaust well.
I wouldn't want to be smelling it.
Oh,
Yeah. Anyway, well done for taking one for the team, Alan.
that's
If you have nitrogen oxides, just set in the old members of the team, they're more and
But if I don't take sniff for the team. It's not quite the same as Professor Lindhoff taking a taste for the team. In the water reactors, you get oils, quite a lot of oil being formed from the I guess it's the fissioning down of oxygen into carbon. So you get long chain hydrocarbon oil formation in the water reactor. And Professor Leonov says it doesn't just feel like the olive oil, it might also taste like olive oil.
Anyway, that's a chemist in us, I'm afraid. Acid. Yeah. It's always the first thing you're ever told to do in the lab. Have a sniff. What's going on?
Yes, exactly. Did you ever try to inject some water mist? Oh, sorry. Yes. Sorry, cheeks. Oh, I thought you were about to inject. Yes. Anyway, yes, we've done it, Anatoly, you just explained earlier that as you increase the water, the moisture amongst water, that you can get a much higher comp, and you can also get a much more powerful reactor because you've got more energy going into the system. Well, very good way of increasing Amazon reactor.
Haslam, what do you use for that? Because in Walt Jenkins' patent, he uses one of these pond foggers.
We use a damp cloth sometimes.
Damp cloth, very good. Try a pond fogger.
Okay, that's a good idea. Yeah. We find direct injection into the air before it goes into the whole vortex thing does just really create enough misting effect, and then it goes through the system. So yes, we didn't need the pond fogger.
No. You could boil a kettle in that corner of the lab near the air intake, actually. That would do it for you.
Exactly, yes. Or wait for it to rain. Because Anatoly, I remember one of your presentations stating that you got a 10 kilowatt heat output. Yeah, it really depends on how we decide to run the reactor. And there is like 100 kilowatt, no, instead of 70 kilo. One is being put together at the moment for a 70 kilowatt direct electricity coming out at the moment, but we keep blowing the capacitors on the power supply unit. So we're having to put more kind of filters on the back end to stop the excess electricity coming and blowing up the power supply unit. But on the water one that Sergey and Oleg have done work on, that one basically is a 70 kilowatts of heat coming out at 40 bar pressure.
On that topic, what's the longest you've had a reactor run for, and has that been repeatable? Within a ballpark.
The reason the reactor times aren't very long is because of this issue regarding the power supply units. One is we're using lab-based power supply units so that we can we can electrically start the unit and then back the power supply unit down and do other little tricks with it. But rather like when you've got an arc light working or an old fluorescent tube working, once we lock into the exact parameters, then we can use much cheaper, much more solid, reliable power supply units. So we've now bought an industrial plasma sputtering power supply unit with a very high power rating. So that unit's got massive fans inside it, so it's designed to operate, on an industrial production line. So we should be able to run the units as long as the power supply units run.
So what has the longest time you've run a reactor for been?
4 hours.
4 hours.
Yeah, I think that was from getting to work to lunchtime, or it's lunchtime to supper time.
Got to stop for lunch.
Yeah. Yes. So yeah, that's I guess now we have an automation system. So we spent a lot of the year working on the automation system so that we can remotely control the devices from one lab to another lab. And that means that we can keep cameras on them, and we can even watch them when we're at lunch.
In Suhath's system in India, he had a thing that was about the size of a wardrobe from a 3-phase supply. But you can see on some of the videos I captured, periodically there was a very large and high UV explosion, which filled the entire lab, and all of the cameras completely whited out. and that tripped his massive supply. So I'm just wondering whether you might see, because effectively he's got pulse to discharge of around the same voltage level as you've got going through flowing water. It's more like plasma flow discharge. So I wonder, if you're going to see some of those when you start upping the power.
On our version of that, the water reactor, we've seen a very constant light emission coming out of it. We haven't seen these big bursts of light coming out of the water flow.
What is the typical sort of frequency spectra of that light?
Past, never looked at it because in the stainless steel vessel,
Okay.
we've done X-ray spectrometry and the optical spectrometry on it. So we've now designed a system so it's got windows both sides, so we can start doing those measurements.
Haslam, the example you gave was the plasma vortex reactor type CMOS type device. What about the direct electricity generator? What kind of status is that, and what kind of output is that getting? Is it predictable? What's the issues with reliability on that?
It's reliably play the capacitors.
Okay.
And what we've done is we've got it basically going into an inductor loop at the moment, so we can measure the electricity out. So around 2 kilowatts, I think, is what we've done to date. 2.25 kilowatts out, or say a kilowatt in electricity, and we're aiming at 7 on that one at the moment.
And same question, how long have they lasted for in a continuous run?
Minutes,
right?
Not more than 2 or 3 minutes.
Okay.
Which don't want to. Power supply units take a long time to order, and they're very expensive. So we haven't got a huge budget for multiple power supply units yet. So we just literally treat them as kid gloves.
Thank you for your honesty there.
Yeah, imagine having the ones we wanted, all those ones in the lab to keep blowing them as rebuilding. It's lovely, but not yet.
Mm-hmm.
Any more questions? Oh, go on, Mike.
If I understand, you had a water system before, and now an air-cooled system now. I'm not sure.
We talk about air cells and water cells and things like that. They're, from my might call the same stable, if that was the right word. It depends very much what you put through the reactor. So, and the power supply units are very similar. Well, one's a water pump, one's an air pump. And the water reactors tend to be pressurized water reactors, whereas the air cells and the hydrogen cells, for example, are running on at atmospheric pressures.
Okay.
Just question of what is the working fluid you're pumping through the machine?
Are you still developing both systems, or?
Yes, there's all 3 or 5 in development, basically, because different people are interested in different devices, it seems. So there's a lot of focus on commercially on just industrial heat, but how we get to the industrial heat is up to the scientists, sort of, and the economists.
Yes.
Like, you're muted, Michael.
Back. Okay. So on the electric units, you might want to go to school and use vacuum tube based power supplies because they might be more resistant to the transient spikes that are trying to get back through the system than modern ones that use semiconductors for the active elements.
Yeah, the problem is we need to be able to control the pulsing very accurately. So now we've got a system whereby I use the analogy of ringing the bell. You can hit the bell, listen to the NDR reactions, and then as the NDR reactions are coming down, you can then send another impulse in. So therefore, you need IGBTs to do that, or MOSFET.
Well, I mean, I'm not sure of the switching speed of those things, but vacuum tubes would work in the old days easily in the 100 megahertz range. So, and at 1500 volts, it seems like
we got a Californian sitting opposite me who's nodding, going, "Yes, I agree." And in the power supply unit we used to use, that was built by Oleg and Sergey and the guys, that was basically using vacuum tubes, big, nice, good-looking vacuum tubes.
I mean, I've got a whole collection which I'm going to sell to some collector. But okay,
Maybe someone to others.
Yeah. Can you say something about the upcoming year? What will be the focus on 2025, and where do you think you will be in 12 months?
Well, hard question. Oh, yeah, it's a good question. I'll answer the technical one in a minute, but I think it's very important because what we're trying to do with Lenaria and the International Society for Condensed Matter and Nuclear Sciences, we're trying to get every week. We try and get as many LNER companies together on a call as possible. So whilst the scientists are debating this wonderful area of science, the commercial guys can start building a momentum, an avalanche effect. So we're trying to make sure that we create as much positive news and outputs as possible. So we're trying to make sure as many companies take working reactors as possible to ICCF 26 in May. So we're Alan's trying to arrange for us to have a little space there as a sort of a trade show, because there's approximately 10 companies now that are really in this LNER space developing commercial prototypes. So from our point of view, our point is to try and have they call them in the commercial world, minimum viable economic products. So our idea is to have a 100 kilowatt MVP commercial heat device ready to start supplying commercial heat to our local companies around here in a year's time. That's our aim. And I think Miura with Clean Planet's probably got a similar aim their end. And I think those are those are the two. I think Orion might be doing something along similar lines again. I'm not sure. Brilliant Light, I don't know what they're doing at the moment, but I think they've got a similar ambition, but I don't know which time frame. And our good friend Andrea Rossi is probably going to be he's also trying to promote an industrial heater, but let's see how he does with his car and this heating and things. No idea.
Static heaters seem to be much easier rather than managing all elaborate.
It's so much less engineering to do. So like around here, we have ceramics companies. They require almost 50% of their energy spent drying ceramics. So it's like 200-300 degrees centigrade they're very happy with, which is our current output. And then if we then heat that with tungsten rods, we can then create 1,500 degrees centigrade, which is what they need for firing. So we should be able to do drying and firing. And literally around here, there's like 100 megawatts easily within 15-minute drive of where I am, which is a loss of it in the R reactor. So that's our focus.
Can you mention something about you've got something in Gibraltar and then you're in Portugal and any other locations?
There's nothing in Gibraltar. It's just a very good hot rock. Was surprised about that. I was. We were discussing it with Carl Page and Dave Nagal at the last conference that at some stage this area, governments will probably try and regulate it. So if we were in the UK at the moment, they would definitely try and stop you exporting this tech at the stage where it is now. And the European Union has very similar regulations, and suddenly the ITARs of the States. So we are currently on the way to Singapore legally. So the intellectual property is Singaporean based, will be Singaporean based. They will give us R&D contracts to develop specific areas of R&D for the Singaporean company. So we will try and stay well away from regulatory compliance, because although Europe and North America would really love this technology, I mean, you look at Africa, I mean, you look at India, I mean, 40% of the population doesn't even have electricity. So whereas LNER reactors are cheap, they're easy to manufacture, people are sitting in their burning cow dung and coal at the moment. This is the technology that could take them out of energy poverty as well as enhance our lifestyle in Europe. So we're looking at and we've talked to the other LNER, some of the other LNER companies. The price of energy coming out of LNER reactors will be around 10 euros a megawatt. That's 5 times cheaper than solar, wind, and oil and gas.
How do you calculate that?
We take the current cost of Alibaba Express core components, because we're nearly all AliExpress. It's 5 times cheaper at AliExpress and 5 times faster. So we take our current supply cost and we basically add depreciation, repairs, and maintenance to it, divide by the number of hours you're going to use it in a year, and it gives you your cost of energy. So standard cost of, that's how you calculate the cost of solar and wind.
Well, what I'm saying is if you can produce 5 times energy 5 times cheaper, all of your input costs are going to drop. It's like a self-feeding virtuous cycle.
Yeah, it's really interesting. Steve Krevich was out here last week doing some from our promo stuff for New Fire Energy in his blog. And he was showing that you just get this you get a beautiful deflationary effect, because at the moment, all the energy companies are driving up energy prices. As soon as you drive down energy prices, then the whole spiral goes downwards again, which would be fantastic. Yeah, that's what people don't usually understand, the effect of energy price rises in economics. It's not good, is it? It just gets worse. So yes, it's working. That way around, because all the cost of all our components are high energy cost components, semiconductors or processed metals. I mean, they were like lithium, but processed copper and processed stainless steel, and those costs will go down dramatically because they're purely energy in material form. Well, I have to go now. Maybe one more question, and I have to go because I've got an investor call, because that's sadly the job. Well, good luck with that. Yes, thank you.
Maybe I have a last question. I sent you an email a few days ago. May I expect an answer?
Jack, can you send it again, please? Because I've got an email flow that's a bit silly at the moment, so I missed a lot of emails. So please send it again.
Okay.
And what is the correct address? What is the correct email? It's the one you've got, hasn't it? Hyphen back. It's the one I use for everything.
Okay.
And Bob, do you want to do a nice video with your video group and stuff like that? Please let us know. We'll lay one on you.
Excellent. Thank you.
And thanks everyone for your support. Thank you, Anatoly.
Yes, it's a pleasure to see you, Anatoly.
Yes, it is.
Thank you. Thanks for a good presentation.
Thank you for showing. 8 minutes.
Thank you. Bye-bye.
Bye, everyone. Merci de tout.
Do svidania.
Bye. Spasibo.
Au revoir.
Au revoir.